Engineering lysine into grains to remediate malnutrition. 80% of the calories consumed in developing countries comes from grains. In developing countries, there is a direct correlation between the highest per capita of grain consumption and malnutrition. The malnutrition stems from grains' lack of iron, zinc, vitamin A, and most importantly, protein. There is an epidemic happening right now because 2 billion people do not have access to proper nourishment. By genetically engineering a grain that has a higher protein content, we can begin addressing the malnutrition problems in developing countries. Malnutrition stems from a protein deficiency specifically linked to minimal amounts of lysine, an essential amino acid. Lysine is considered an essential amino acid because the body does not have the ability to produce it. Thus, it needs to be consumed via diet. Lysine is abundant in animal products, but developing and poor countries do not have access to such food sources. Thus, their diet consists mainly of grains, which do not provide the essential amino acid. Eventually, by altering the genetic makeup of grains, the nutritional content can be improved, creating a grain that provides well-rounded nourishment. For centuries, the genome of living things has been altered to possess favorable traits by selectively breeding over generations. Compared to selective breeding, genetic engineering opens the doors to immediate results and precise altercations. The practice of genetic engineering leads to designing foods nutritionally and agriculturally superior. The Golden Rice Project, which began in 2012, set out to create a grain that is rich in vitamin A, specifically beta-carotene, the compound that gives carrots their orange hue. By the addition of the beta-carotene biosynthesis gene, golden rice now produces an orange pigment in the endosperm, yielding a grain with high levels of bioavailable vitamin A. In the image, you can see the progress of golden rice. The newest generation of golden rice provides the optimal amount of vitamin A needed as a dietary supplement. Like the biosynthesis pathway of beta-carotene was altered, we can do the same thing to manipulate the lysine content in grains. A pathway has been identified that provides an increased amount of lysine within grains. In the biosynthetic pathway of lysine, there are two key enzymes that directly correlate to lysine production. Lysine production is turned on/off depending on the feedback receptors located on those enzymes. When the receptors sense enough lysine in the environment, the production is ceased. By manipulating the sensitivity of those receptors, more lysine can be present before the receptors tell the enzymes to turn off the lysine production. The result of the mutation provides a grain with increased levels of lysine. Although effective, the process has not yet proved to be efficient due to the compensation in growth yield. As a staple food source in developing countries, it is vital that we make a grain that is nutritionally sustainable. Genetic engineering leads to the possibility of finally being able to address the world's malnutrition epidemic by creating a grain that provides adequate amounts of what it nutritionally lacks.